All right, so how does this work? This is the important thing. So I would call this a speed-up plugin. So you don't change any single line of code of the actual VM. So you just load this as an extension to the VM. Okay. So it would be great if all programs had this kind of plugin. So in Vista, you would load like the speedup plugin, and it will run really fast. But unfortunately, not all programs have this kind of speedup plugin. So yeah. Okay, so we hook in the bytecode executor, as opposed with bytecode caches, which hook in the compiler. So we receive bytecodes as input, and then instead of interpreting them, we JIT compile it. Wait. Also, we update the state of the VM so that we can use the old interpreter or JIT. So, because for example, you may not want to JIT compile everything, because if you call like the eval function to eval some short piece of code, probably you don't want to compile it. Also, you may also want to JIT compile only hot pieces of code. So we allow that to be done. Okay, so how does this really work? So offline, when you install the extension, we compile the bytecode handlers to LLVM bitcode and then optimize it. So every single bytecode handler is compiled to a big LLVM file. This file is about 2 megabytes. So, and we then load this file at runtime. Okay, then we translate each bytecode to its handler call, which you'll see. Okay, let me advance here. Okay, so let me advance to here. So we replace this function. Okay, so we receive the bytecode, and then we replace this function so that we can JIT compile things. Let me just, okay, I have here. Okay, so how the current executor looks like. So it is a very simple interpreter. So while true, do stuff. So what's in here? So this is the current bytecode that is being executed, and then we just call the handler that is capable of interpreting that specific bytecode. So this is just a function pointer which is cached for that specific bytecode. Then we look for the result, because like 0 means go on, 1 means stop the VM, and so on. The thing is that most opcodes return 0. For example, add never stops the execution. So when we JIT compile and run the LLVM optimization, we can also remove that switch, because we know that the handler always returns 0, for example. So JIT compiling also has the benefit that we remove a lot of code from being executed. Okay, so let's see an example. So let's try to compile this file to bitcode. So we have the smaller handler here. So let's compile it to bitcode. Okay, so what we do, we have this helper function, which is just a one-liner function, so that's a real problem. So, and then we call here the handler, which is going to execute that bytecode according to the parameters that are here, like the operands. These operands are in this structure. Then we do the switch that's here. We do this switch, but these will be removed by LLVM optimizations because E smaller never returns this value. So this will be removed automatically by LLVM. Okay. So this is a compilation of this bytecode here. So E smaller gets translated to these 3 lines, which is kind of nice. Okay, a more difficult one is this jump, because jump updates the program counter. So we have to, that's a special case. So we use this runtime helper, which is also a one-liner, and then we have to switch and do this if to see to where we are going to jump. Okay. Now, the interesting part, the result. So, if you see, vanilla is the current PHP implementation, and here is the best we can do, which is a nice performance. We get a slowdown. But let me first explain this result. So this is the time to run a simple hello world program one time. So this time accounts for setting the JIT machinery, compile the function, optimize it, and so on. So this is not that bad. Why? Because in PHP, what we want is like to compile a script once and then serve like 1,000 HTTP clients with the same compiled program. So this is not that bad because the execution time is really small when compared with that. I don't have here the time to execute the function, but I forgot to